Hello and welcome to another episode of Study Session for AP Physics 1. In this video we'll be covering Newton's laws and forces and pretty much the whole shebang. So first, getting started, we have to cover Newton's three laws. So the first law is the law of inertia. It essentially says if you have an object that's not moving, it's not going to start moving unless you apply a external force to it. Or if you have an object that is moving, it's not going to stop moving unless you apply like a force in another direction, or it's not going to change directions unless you apply an external force. Second law is force equals mass times acceleration, and it's really net force equals mass times acceleration. So that essentially says that your net force will be equal to your mass times acceleration. And the third law is for every action there's an equal opposite reaction. So if I have this box and I push against the box with the force of 5 newtons, the box will push back against me with 5 newtons. Same principle for gravity. If this is a satellite and it's attracted to the Earth, let's just say 100 newtons, it will be attracting the Earth with 100 newtons. And you might ask, well, the satellites, get pretty attracted to Earth. Why isn't the Earth, moving towards the satellite? Well, the thing is, the Earth's mass is so incredibly large. This net force equals mass times acceleration. So if we have a super large mass, so super big M, and our force is only 100 newtons, so 100 newtons by big M, your acceleration is going to be very small. So that's the main reason why, and in fact that is the reason why. Okay, so let's get into some practice problems. Okay, so the first one states that a person is standing on a horizontal floor, feels two forces. Okay, so this is the horizontal floor. It feels a downward pull of gravity. So let's just draw a free body diagram. Downward pull of gravity, so F, G. Okay, and the upward supporting force from the floor. Okay, and then these two are both equal to each other, so equal in opposite directions. It says these two forces, so our possible answer choices are of equal magnitudes and form an action-reaction pair, have equal magnitudes but do not form an action-reaction pair, have unequal magnitudes and form an action-reaction pair, and then have unequal magnitudes and do not form an action-reaction pair. And the correct answer in this case is, so the correct answer, sorry, I had to quickly pause the video to go do something. The correct answer in this case is that they are of equal magnitudes because the person is not accelerating because force equals mass times acceleration, but they are not an action-reaction pair. And why this is so an action-reaction pair, essentially, it would be like that satellite example I gave on earlier. The satellite, or the Earth pulls on the satellite and the satellite pulls on the Earth. In this case, you have gravity pulling on the person, but then you have force of the normal force pushing up on the person. So both of the forces are acting on the person. It's not like the normal force acts on gravity and the gravitational force acts on the normal force or whatnot. It would have to have like the surface or whatever, if like for some reason the surface still exerted like the normal force or whatnot in the opposite direction of gravity. But yeah, that's why they're not an action-reaction pair, because they're both acting on the same object, and you can't have that. They have to be acting on each other. So yeah. Quickly erase all that. Okay, so the next question is, a person who weighs 800 newtons, okay, steps on a scale that is in the floor of an elevator car. Okay, so we're going to draw an elevator. We got the scale, and we've got the person. Okay, the elevator accelerates upward at a rate of 5 meters per second squared, so it's accelerating upward at 5 meters per second squared. Okay, and it wants to know what the scale will read. Okay, so the thing we have to know, scales always read normal force. And if we were going to draw a free body diagram for this thing, for this situation, we know that we have an upward acceleration of 5 meters per second squared. So our normal force must be greater than our gravitational force. So we have F, N, and then F, G. Okay, and we know our gravitational force will be 800 newtons. Okay, so we can write this as, force, net force equals MA, net force, equals Fn minus 800 equals, and then this, to solve for the mass, it's 800, and then I'm just going to divide by 10 because 10 is close enough to 9.8 to where I can make an approximation, 10, and then our acceleration would be 5. Okay, so we've got Fn minus 800 equals 50. So Fn from that equals 850. So that should be, hold up one second. For some reason, oh my goodness, yeah. I don't know why I did this. 800 divided by 10 to solve for our mass is 80 kilograms. So this 10 right here, and for that matter, which will change these other like sequential steps beyond them, because it's like 850. Now that doesn't seem right. What did I do here? That the mass is 80. 800 divided by 10 equals 80, doesn't it equal 10? So that's 80 times 5, which is equal to 400. So 400 plus 800 is 1200, and that is the correct answer. I was like, man, 850. That doesn't seem right. I mean, that's where it sometimes helps to have done a lot of these problems, because you're like, no, that numbers are not right. And sometimes whenever you're just a goober and you write 800 divided by 10 is 10, well, that's that problem. We're just gonna pretend that didn't happen. That was embarrassing. That was real embarrassing. Okay, so the next problem says a frictionless incline with a length of 20 meters. Okay, 20 meters. And I'm just gonna write no friction. Has a maximum vertical height of 5 meters. Okay, and if an object of mass 2 kilograms. Okay, so we've got this mass on here, and the mass equals 2 kg. Is placed on the plane, which of the following best approximates the net force it feels? Okay, so this is an inclined plane problem. And first off, we know that this, you know what, let's just draw the free body diagram. Okay, so in this case, we're going to have our gravitational force that points down. I'm just drawing that really long. It doesn't really matter how long as you draw it, as long as it's like relatively, as long as it's like the appropriate size relative to the other arrows. And we've got our normal force that's coming, oh, that was a bad line. Our normal force that's going perpendicular to this plane. Okay, so here's what we have to do. So we know that this angle, or at least the sine of that angle is equal to 5 over 20 or 1 over 4. So let's just say the sine of that angle is that. Okay, so we know that if we carry on like this normal force line, you know what, I'm not even going to call that 1 over 4 for now. I'm just going to leave that angle there, and then I'll use that later. Okay, we carry on our normal force line if we connect it there. Okay, so we know that this whole angle, because it's perpendicular to the plane right here, this is a right angle as well. We know that this is a right angle, so this interior angle of that triangle will have to be 90 minus theta. Okay, but then this whole thing also equals 90, so we know that this has to be theta. So from there, we can say that the sine of theta, so opposite of our hypotenuse, so the component going parallel with this plane, I know that line is not parallel, but it really should be parallel, will be equal to our force of gravity, our net gravitational force going down the plane. So we can rewrite that as sine of this angle, which we know is 5 over 20 equals 1 over 4. Okay, so if we do 1 over 4 times your mass, which is 2, times gravity, which is, we'll just call 10, that will turn into, what do you call it? This whole thing's 20, and then 20 over 4 equals 5 newtons. So yeah, and we know that the y component of that will cancel out with the normal force. Okay, so 20 Newton block. Okay, 20 Newton block is being pushed across a horizontal table by an 18 Newton force. Okay, if the coefficient of kinetic friction between the block and the table is 0.4, so we know that mu equals 0.4. Mu doesn't have units because it's a ratio. It says find the acceleration of the block. Okay, so we know that your force of friction will equal mu times your force of normal. Okay, so that equals, so force of friction equals 0.4 times 20. So that's 4 over 10 times 20. Okay, so that's 8. Because that would cancel and you just have 2 times that. So that's 8 newtons, okay, going that way, because frictional force always opposes motion. So we know that our net force equals 10 newtons equals mass times acceleration. And this time, I'm going to get the mass right. So 20 divided by 10 equals 2, not 10. So we've got 2 kilograms times acceleration. So 10 divided by, that should be an equal sign, 2 equals 5 meters per second squared. Okay. Next problem. Okay, so the coefficient of static friction, okay, so mu, I'm going to call this mu s, equals 0.5. Okay, the ramp's incline is an angle of 30 degrees, and the box is placed at rest on the ramp. The box will do which of the following? Okay, so let's quickly draw a ramp so we can get, some, this one, we don't have actual numbers. We're going to have to do some formula manipulation to solve this. Okay, so we've got this, we've got a gravitational, boom, boom. Okay, so we know that our gravitational force down the ramp will be equal to Fg sine of theta. And since sine of 30 degrees is 1/2 equals 1/2 times mass times gravity, because that's Fg. Okay, so we know that that's the gravitational force down the ramp. Okay, so remember our frictional force equals mu Fn, and Fn equals mg cosine of theta. Okay, so Fn equals mg times square root of 3 over 2, because that's cosine of 30, and then multiply that by 1/2. Okay, so 1/2 times mg times square root of 3 over 2. Okay, and then also, so that gives us the maximum static friction, because your static friction, it only counters however much force you have. But yeah, so our maximum static friction, so if we look at this, okay, so we've got 1/2 times, so 1/2, if we're trying to compare one which is larger, we could cancel, or we could like take that factor out, we could take the mg out, So we have, is 1 bigger, or is square root of 3 over 2 bigger? Square root of 3 over 2. And the correct answer is square root of 3 over 2 is actually bigger, because, what do you call it? You're multiplying it by a factor that's, this is greater than 1, because square root of 3 or whatnot. It's kind of hard to explain, but like if I quickly just do square root of 3 over 2. Sorry about that. On my key, it had said that it would not move. So I was like, okay, well, based off the math, square root of 3 over 2 would have to be greater than 1. But whenever I looked back at my key, I realized the key was wrong. Because square root of 3 over 2, this is what I was thinking, this is what I was kind of starting. So square root of 3 over 2 has to be less than 1, because square root of 3 is less than square root of 4. Square root of 4 equals 2, and 2 over 2 equals 1. So this will actually accelerate down the ramp. So what I had originally said about square root of 3 over 2 being greater than 1, that's just simply false. I don't know why my key was marked wrong in my book, but I found the actual key, and for some reason, like I had all the answers marked on the book, but I must have just mismarked it the first time I went through. I'm like, no, it should move or whatever. But I went back and I checked it, and it does move. It accelerates down the ramp because the net force is greater than there is a net force, so you're gonna have acceleration. Yeah. So like basically I solved it right on here, but I just can't like circle. Man, it's been a rough video. Okay, let's do one more. So assuming a frictionless massless pulley, determine the acceleration of the blocks when they are released from rest. Okay, so we've got this pulley. Okay. We have big M and little m. Okay, so your net force equals big M times G minus little m times G. Okay, because your tensional force will be the same, or whatnot, and they will cancel out in direction, so that this is your net force. Okay, so that equals mass, which is big M, plus little m times acceleration. So our acceleration simply equals big M times g minus little m times g over big M, big M plus little m. And you can rewrite that as big M minus little m over big M plus little m times g. Alright, well, hopefully, even though this video is a bit rough, and I just made some dumb mistakes, hopefully you learned something, and hopefully this helped. If you have any more questions, be sure to visit my website, studysession.org. The link will be in the description. I will be happy to answer them, and hopefully I won't make a dumb mistake whenever I do answer them. But make sure you guys stay tuned. I will be uploading more videos soon. And yeah, that's pretty much it.